bond enthalpies. Let's start with the definition. The definition of bond enthalpy is the energy required to break 1 mole of a bond in the gas phase. Consider a molecule consisting of 2 atoms joined together. The bond enthalpy is the amount of energy required to break the molecule into 2 separate atoms. In order to break a chemical bond, we have to put energy in to overcome the attractive force between the 2 atoms. Thus, bond enthalpies are always positive. The bond enthalpy for this reaction would be given in kilojoules per mole, and remember it would be a positive number. That is, the reaction is endothermic. Conversely, when a chemical bond is formed, energy is released. Bond breaking is an exothermic process. So, to recap, bond breaking is an endothermic process. Energy is added. Bond forming is an exothermic process. Energy is released. You could remember this by using the mnemonic Ben-Fox. Making or breaking the same chemical bond will require the same energy to be released or added. The values for bond enthalpies are found on page 10 of the databook. You'll notice that 2 tables are given. One table is given for bond enthalpies, the other for mean bond enthalpies. Why is it that for some bonds the bond enthalpy is given and for others the mean bond enthalpy is given? Have a look at the bonds in the table for a while and see if you can figure out why. Did you spot a pattern? All the bonds in the table of bond enthalpies are in complete molecules, whereas all the bonds in the table on the right could be part of a number of molecules. Let's explain this in a bit more detail, and we'll use butanol as an example. Butanol has 3 carbon-carbon single bonds, 1, 2, and 3. However, they are all slightly different. Bond number 1 is at the end of the chain. Also, the first carbon is bonded to 3 hydrogen atoms. But the second carbon atom is bonded to 2 hydrogen atoms and a carbon atom. The second bond is different. Look at the atoms that the carbon is bonded to. They are different from the first. Finally, look at the third bond. One of the carbon atoms is bonded to 1 carbon and 2 hydrogen atoms, whereas the next one is bonded to an oxygen atom and 2 hydrogen atoms. The energy required to break these bonds is going to be slightly different. It's going to be different again for similar bonds in different molecules, such as propane. However, it is difficult to determine the bond enthalpy for a specific bond experimentally. However, the average for a carbon-carbon bond can be measured for lots of different molecules, and this is a good enough estimate. Let's summarise what we've learned so far. Bond breaking is an endothermic process. It is necessary to add energy to break a chemical bond to overcome the attractive force. Bond forming is an exothermic process. Energy is released when a chemical bond is formed. Bond enthalpy measures the energy required to break 1 mole of bond in the gas phase. The mean bond enthalpy is an average of the bond enthalpies for the same bonds that appear in different molecules or a different place in the same molecule. And bond enthalpy is always positive. We can use bond enthalpies to estimate the enthalpy of reaction by subtracting the total enthalpies of the bonds formed away from the total enthalpies of the bonds broken. This is easier to see with an example, so let's use the combustion of methane. We start with a balanced equation for the combustion of methane. 1 mole of CH4 burns with 2 moles of O2 to give 1 mole of CO2 and 2 moles of water. It's very important that the equation is balanced correctly before we start. Let's look at the exact molecules involved in this equation. 1 molecule of methane, 2 molecules of oxygen, 1 molecule of carbon dioxide, and 2 molecules of water. First, let's look at the bonds being broken. We'll start with methane. Methane has 4 CH bonds, which are all broken in the reaction. 1, 2, 3, 4. That's 4 CH single bonds. Oxygen has 1 double bond, but there are 2 molecules in the reaction. 1, 2. So that's 2 oxygen-oxygen double bonds. Now let's look at the new bonds being formed. There is 1 molecule of carbon dioxide, which has 2 CO double bonds. 1, 2. And finally, we have 2 molecules of water. So that's 1, 2, 3, 4 new OH single bonds. Now it's time to calculate the sums of the bond enthalpies on each side of the equation. We'll start with the CH single bonds. The mean bond enthalpy can be found by looking in your data book, page 10. It's 412 kilojoules per mole. We have 4 of them, so let's multiply that number by 4 to give us 1,648 kilojoules per mole. Next, the oxygen molecules. The bond enthalpy for an OO double bond is 498 kilojoules per mole. Multiply that by 2 because we have 2 oxygen molecules and we get 996 kilojoules per mole. Now, bond forming. The mean bond enthalpy for a carbon-oxygen double bond is 743 kilojoules per mole. We need to form 2 new bonds, so that means 2 times 743, which equals 1,486 kilojoules per mole. Finally, water. We have 2 molecules, each with 2 new OH single bonds, each with a mean bond enthalpy of 463 kilojoules per mole. So 4 times 463 gives us 1,852 kilojoules per mole. Let's add up the total enthalpies of the bonds broken. 1,648 plus 996 gives 2,644 kilojoules per mole. Now we add up the total enthalpies of the bonds formed. 1,486 plus 1,852 equals 3,338 kilojoules per mole. Now, the enthalpy of reaction is given by the sum of the enthalpies of the bonds broken, take away the sum of the enthalpies of the bonds formed. 2,644 minus 3,338 equals negative 694 kilojoules per mole for the enthalpy of combustion of methane.